Thank you, Enyo. Good morning, everybody. Yeah, so I'm going to talk about this tension, which is now 6.4 sigma tension. That's when you compare the measurement of H naught, assuming lambda CDM, with the most recent combination of CMB data, including the latest ACT and SPT release, with the most recent measurement of H naught from shoes, which is from a bit more than 1 year ago. And so this is really not just a tension between Planck and shoes or CMB and shoes. It's a more general thing. It appears when you look at when you compare different types of measurement of H naught. For instance, the tension would still be there, although with maybe a smaller significance, if you would replace shoes by other measurement of H naught from TRGB, from the CCHP experiment, from strong lensing, from other calibrators like the comma distance. And it would subsist if you would replace CMB experiment by a determination of H naught from, for instance, combination of BBN and BAO data. So it's a general thing. It's very worrisome. So the big question is this systematics in the data, or does it require new physics? And of course, I'm not able to answer this question today. Nobody is. It's a very delicate issue. There is no trivial answer. The only thing I can do is to try to give a fair summary of what is going on and what people tend to think. So first, you might be under the impression that last summer there was an indication that the tension would disappear when CCHP, the Carnegie Chicago experiment, released a paper in which they said that they were comparing 3 methods to calibrate supernova luminosity with different calibrators, so different standard candles, which are Cepheids and JAGB and TRGB, which are quantities you infer from the color luminosity diagram of stars. And in a paper from the last summer, Friedman et al. Were advertising that these 3 different methods give 3 different results, with Cepheids giving the largest H naught and JHGB the lowest one. And at the beginning, people were under the impression that this was a crucial piece of information showing that these different calibrators are contaminated by systematics because they don't even agree with each other, which would be really the proof that there would be some unknown systematics. And after all, if Cepheids would be systematic dominated and JGB would bring the right answer, then from a plot like this, you would say, okay, the tension is on the edge of completely disappearing. But this is really not the case, because after this paper, there have been some intense work, both from the shoes and the CCHP team, to better understand the origin of this shift. And the origin of this shift is actually not a contradiction between the different calibrators, Cepheids, JGB, TRGB. And one way to be sure of it is to look at special host galaxies, where in the same galaxy, you can see at least 2, or if not 3, of such, you can use 2 or 3 of these calibration methods. And when this is the case, the different determination of the distance from Cepheids, JGB, or TRGB always perfectly agrees. Instead, it was understood that the shift between the 3 results is due to something completely different. It's the fact that in this particular analysis, or in the first version of this analysis, the population of host galaxies that was used to calibrate with one of the 3 calibrators were not representative sample and could easily be shown to be biased with respect to each other. In other words, this was not a discrepancy due to the physics of the calibrators, but to selection effects. And there was an effort to compensate for this or to cancel these selection effects. So there were many publications from the shoes team and collaborators of shoes where they tried to use their own GAGB or TRGB calibrators, and they found that all methods are consistent with each other, but never as precise as what they get with Cepheids. And also in the published version of the CCHP paper, the plot that I is no longer there because they acknowledged and they agreed that there were selection effects. And instead, the focus of the paper is more on demonstrating that when you try to calibrate supernovae or the standardized magnitude of supernovae from GAGB or TRGB, or even Cepheids, you do get consistent answer. So this evidence for a problem went away in some sense. So the problem is still there. And as you have seen in the previous plots, this one, when the SHOES collaboration tries to use JGB or TRGB from the James Webb Telescope in order to calibrate supernovae, instead of their traditional Cepheid method, they get a very wide error bar. So there were publications by SHOES recently where they add TRGB calibrated calibration on top of Cepheid calibration. It does not change their results significantly because their result is always dominated by Cepheids. But what is interesting is that in August, there was a release by a completely independent group. This is not SHOES, this is not CCHP, it's a group where the first author is Max Newman from Rutgers University. And this group have a measurement of H0 based only on the TRGB calibrator. It's completely independent. And they find, again, a very large H0 with an error bar, which is 3 times bigger than the SHOES error bar, but which is still not bad. And so from TRGB only, it seems you do have a Hubble tension, again, which is quite significant. On the side of the SHOES collaboration, they have not really improved their measurement till 2024, but they have cleaned the analysis of possible sources of systematics. And in particular, there is a worrisome systematic in this business, which is called crowding. So when you look at a Cepheid, you want to measure its period in order to know the absolute luminosity. But of course, you want also to measure the mean or the average apparent luminosity in order to get the distance. And this second measurement is delicate because in a pixel of your data, you see a variation of luminosity in a big pixel or in a few pixels, and you are never sure that the luminosity you measure comes from one Cepheid alone or one Cepheid plus light from another star, which is almost aligned with a Cepheid. This effect is called crowding. It could lead to a wrong estimate of the apparent luminosity of supernova, and thus a wrong estimate of their distance. And for some time, people believe that this could be the systematic that would be at the origin of the Hubble tension. Then the SHOES and CCHP collaboration had arguments to show that it should be a small effect and to correct for it to some extent. But a lot of progress has been done with the JWST telescope for several reasons. First, now when you look at the same Cepheid, for instance, at the center of this pixel, there is the same Cepheid seen by HST and GWST. And due to the much better angular resolution, it's much easier now to isolate the light coming from really a single object and be sure it's not contaminated by another one. And there was another argument published recently by the SHOES team, because they were lucky to observe a very special galaxies which has a tidal host. So this is a main galaxy, this is a tidal host, and we know that they are really close to each other, so from our point of view, essentially at the same distance from each other. This galaxy is a typical type of galaxies that is usually being used in order to calibrate supernovae from Cepheids. So it's a typical host galaxy with Cepheids. Because it's old, it has a big background of stars. And when you zoom on a region of it, you see that it's very dense. And there could be potentially some crowding effect. But in the tidal host, it's a much younger object with much less background. And it's clear that the Cepheids that you observe in this object cannot be contaminated by crowding. The image you get from Cepheids in this object, which is here on the right, is very pure, and there are no other stars close to the line of sight of the Cepheids. And what the SHOES team showed is that when you do a calibration of the Cepheids from either of the two objects, you get the same result, which is a proof that crowding was not really an issue and a serious source of systematics. And in particular, they get a lot of data from JWST, which is completely crowding safe. So they have not changed their measurement and their error bar, but they have just ruled out in a convincing way crowding as a possible source of systematics. So this is a summary, and if you want if you are not specialists like me, and you want a very nice pedagogical update on the observational status, you can watch a really nice seminar that I saw last week by Louise Broyval, and it was given in the context of the Cosmoverse webinars, and it has been posted on YouTube yesterday. It's 45 minutes, and it's very complete and very easy to follow. Yeah. They have a lower central value and a large error bar, and they no longer claim this shift between different calibrators. So they agree with everybody. They agree with the large value and the low value. They have a central value which is around 70, and they are no longer claiming a central value of 68 with JGB, because this was based on a non-representative sample, and when you correct for this, the central value moves around 70 again. Yeah, sure. Okay, so on top of this, okay, we have a multiplication of tensions in cosmology, and the situation is really becoming embarrassing. So we have talked for a long time about the S8 tension on the amplitude of the power spectrum from weak lensing. This tends to be slowly going away. You know that the last analysis of Keats, a Keats legacy paper, claims no significant tension. DES is still at 2-ish sigma tension level, no more. So this is no longer a big concern. People were worried for a while about this lensing anomaly in Planck data, meaning that the temperature spectrum essentially appeared as so smooth that there seemed to be like some spurious source of lensing of the data. This has gone away. It's less clear with the last Planck data analysis by various groups, and ACT and SPT do not find this. So this is essentially gone. But we have this other tension that came from the recent DAISY measurements, which in the lambda CDM model, you would interpret primarily as a tension on big omega m. That you should think in this context not as a parameter for the density of matter, but really it's omega m equal 1 minus omega lambda. It's a parameter that tells you when you switch from matter domination to lambda domination. And the possible solution for this, as you know, is dynamical dark energy. And actually, if you don't assume dynamical dark energy, but you are convinced that the DAISY results are fully correct with correct error bars, then you anyway get a problem with the neutrino mass, because the upper bound that you get for the neutrino mass is ruling out the minimal value of neutrino mass from neutrino oscillation at the 2-3 sigma level. So there is something odd going on here. Yeah. Yeah. Yeah, because the tension on omega m will give you a tension on S8, because S8 contains omega m. Yeah. So one possibility is that we get a multiplication of tension, because there is a general trend in the astrophysical community to underestimate errors, and the errors from both sides should be larger in reality. Or maybe these tensions are different hints of the same new physics and the need to go to another standard cosmological model. And the big question at the moment is to find out which of the two is correct. And now I talked a bit about observations. Now I will go to the theoretical side and say, okay, let's assume there are no unknown systematics. We take all the data set as they are, and we wonder if we can explain this tension by a change in the cosmology. What is the price we need to pay? Are there working models? If they are they elegant or ad hoc and fine-tuned? Okay, you can guess what will be the answer. But we are going to go through it and summarize the situation. Okay, so We measure standard rulers and standard candle distances, and the Hubble tension is about a disagreement between the two, essentially. So to know the distance to redshift relation, you use a standard relation for a Friedman universe. And then if you have computed this, in principle, the angular diameter distance is immediately given because we have this distance duality relation, which is very, very general. To break it, you would need some very special theories of gravities. I will come back to it. Or some, if you want to break it at a fundamental level, you would do it through modified gravity, but really not the usual modified gravity model. Or you can break it effectively by looking at a model where just when photons travel along their geodesic, the flux is not conserved for some reason, and this would affect the luminosity distance or the effective luminosity distance, but not the angular distance. So we will come back to this distance duality relation in a few slides. So now the tension comes from two ways to determine the Hubble radius, from either distance ladders or inverse distance ladders. So with distance ladders, what do? You look at these objects for which you have different ways to measure the distance. And close to you, you look at objects where you have direct geometrical measurement, for instance, from the parallax, that can be used in combination with the observation of uncalibrated standard candles like Cepheids or TRGB or GAGB. And because you have the two, you calibrate your standard candles. For instance, you find the relation between Cepheid luminosity and period. So this is done in the so-called rung 1 of the distance ladder technique. Then in rung 2, people look at host galaxies where you find again the same calibrators together with supernovae, and then you use it to calibrate your supernovae luminosity. And then you look at supernovae, so this is rung 2. And then in rung 3, you look at supernovae that are further away. They are far away to be in the Hubble flow, but not too far away in order to be a probe of H0 and not of the acceleration of the universe and dark energy, and you get your measurements. But so using rung 1 and rung 2, what you do is to find the standardized luminosity or magnitude. And you will use it in combination with a measurement of these distant supernovae in rung 3, for which what you measure primarily is a luminosity distance up to an unknown calibration parameter, which is a standard supernova luminosity. And then when you use a combination of information from the first two rungs, so you measure L, and the third rung where you measure this ratio, you have a direct measurement of dL of Z. And from this dL of Z, you look at the slope and you have H0. For inverse distance ladder instead you will calibrate everything at very high redshift. So you look at what you want to calibrate is the sound horizon in the early universe. And the sound horizon is very easy to predict in a given cosmology. For this, you need to know essentially the baryon and matter density. And the height of the peaks in the CMB give you an estimate of the baryon and matter density. So it gives you an estimate of the sound horizon in the early universe. But the crucial point, the absolute that will be dominant for all the discussion, is that this prediction of ds as a function of baryon and matter density is very model dependent. It would be different when you add additional dark radiation or when you do various things. But assuming that you have predicted ds in this way, you can then use it in combination with a measurement of peak scale or BAO scale in the correlation function of galaxies or in the CMB spectrum. And by looking at the scale perpendicular or along the line of sight in galaxy maps, or just perpendicular to the line of sight on the CMB last scattering surface, you get a measurement of the angular diameter distance normalized to ds, or h of z normalized to ds. And then when you combine the two, you combine your model prediction for ds with these measurements, you get dA of z and h of z. So now let us think of the redshift which are involved in these two techniques. So to calibrate your sound horizon, you use CMB data, which is a probe of ds at a redshift of 1000. Instead, you can predict the sound horizon with a combination of BBN and other data without the CMB. And then you calibrate your DS at even larger redshift. And once you have calibrated your DS, you look at the angular scale of the sound horizon in the CMB or in BAO data, and then you get measurement of dA of Z, in the case of BAO at redshift around 1 and CMB at 10 to the 3. So this is an estimate of dA of Z calibrated to high redshift, and this is why it's called the inverse distance ladder. With the distance ladder, you calibrate your supernova luminosity at small redshift using essentially object at a redshift smaller than 10 to the minus 2. And you use this calibration to infer dL of Z by looking at supernovae, which are scattered from 10 to the minus 2 to more than 1. So this is called the distance ladder. And at the end, the Hubble tension is a tension between the value of H today, so that you extrapolate from either dL of Z or dA of Z when you go to the limit Z equals 0. So it's a tension between the starting point of dL of Z calibrated to supernova luminosity using distance ladder, or to dA and H of Z from BAO and CMB calibrated to the sound horizon, but assuming a given model in order to predict this DS. So that's really what the tension is about. And to solve this tension, people have tried to play with the theoretical model, following essentially 4 routes. And I will describe these 4 routes before mentioning concrete examples. The first route, sorry that the titles are not perfectly visible, so I call it category 1 here. It's about modifying only the late background expansion history. And the idea is that we measure the luminosity distance, dL of Z, with supernova. This luminosity distance, you have an integral over H of Z. And of course, you can play with a function. You can change a function while keeping integrals over this function constant to some extent. So the first category says, okay, I'm going to tailor my expansion rate such that it's higher than expected today, but then it's depleted in such a way that the integral over 1 over hz is essentially the same, and I'm still compatible with my data. And this was working up to some extent in the old days, or until a few years ago, essentially when there was not a big overlap with a measurement, with a redshift at which you measure supernovae and BAO. So when there was not a big overlap, you could tailor your H of Z in order to start from a large H naught, then go through the dL of Z of all supernovae, and then something would happen such that you would go through the dA of Z of the BAO up to the CMB measurement of dA of Z. And this would work for a while. Now it doesn't work because you have a direct contradiction between the information on dL of Z and dA of Z at the same redshift from supernovae and BAO. So suppose I do the standard thing, which is to calibrate my angular distance to ds from the CMB or BAO plus BBN, assuming lambda CDM. I calibrate my luminosity distance to MB from shoes. Then I can see this direct contradiction. It was shown in a nice plot by Vivian Poulin and collaborators last summer. They show you here dL of Z and 1 plus Z squared dA of Z, which are supposed to be the same in most cosmologies. They don't show directly these quantities, but the residual of these quantities compared to a reference lambda CDM model. But it doesn't matter. What you should get this plot is that the red agree at the same redshift. There is a wide range and addiction with each other. So this is our function. What you do the modified late background expansion. We'll move the blue and red points all together, but respecting the distance duality relation. And so you will always get this offset between the two techniques. So this doesn't work. In category 2, you say, okay, well, because it's a problem between the angular and luminosity distance, I'm going just to assume that both measurements are perfectly correct, and MB and DS from CMB and shoes are perfectly correct. It's just that I'm not supposed to find the same because for some fundamental reason, my distance duality relation is violated. So there would be a way to do it without fundamental physics. It's just assuming that the light coming from supernovae is dimmed by absorption by dust. This has been thought for a long time, and observers exclude this possibility. They do tests by observing the supernovae in various color bands or by taking some spectra. And they say that it's completely clear that there is no significant effect of absorption by dust. So this relation would need to be violated at a more fundamental effects. And there was an idea that was already, okay, so let me tell you then how this could be violated. We said with very unusual gravity theory. Really very unusual because first you need either to give up the idea that gravity is described by a Riemannian framework or pseudo-Riemannian, where the connection is a Levi-Civita connection. You need a more complicated formulation of curvature based on torsion. So this is going quite far. Another way to violate this relation with gravity is to have a complicated gravity action where the trajectory of a photon will depend both on its initial position and momentum. So you lose the unicity of geodesics. So this is going really very far, and not many people are ready to go to such a step. So the other possibility to violate this relation is to have non-conservation of the photon number along a given geodesic. And one way to do it would be to have photon interacting with axions. And this is an old idea that has been studied in the past, and it's very constrained by different things. I mean, you should preserve the black body shape of the CMB. You should preserve the observed quasar spectra. You should be compatible with laboratory bounds on axion-like particles. You should not disturb too much the physics of supernova explosion, which is compatible with a standard model. So this has been looked in the past, but initially in a different context. When people claimed that the universe was accelerating because of distant supernovae, immediately some theories said, no, there is no acceleration, there is no lambda. What we have just is supernova dimming because some of the photons from the distant supernova oscillate into axions along the line of sight or decay into axions. And this has been ruled out to a large extent by these other constraints. But now people want to try to use the same argument in a different context where you are not trying to explain the acceleration of the universe, but just the luminosity of closer supernovae, which are in the rung 3 of shoes and which are used to measure H0. And for this, you need the opposite. In order to explain the acceleration, you needed supernovae dimming. In order to solve the Hubble tension, you will need an enhancement of the light from supernovae. So you could go to very crazy ideas like supernovae are emitting both axions and photons, and some of the axions get converted into photons along the way. But even in this kind of model, you would be very constrained by the different bounds. And moreover, there is a simple way to see that this is not favored. If this would be the right mechanism, then you would explain the enhancement of supernova luminosity to be larger for the distant supernovae and smaller for the nearer supernovae. And this is not indicated by the data. When you play with these models, what you see is that you need a constant offset between DL and DA, and not an offset that would be growing with redshift. And this is really an indication that it's a matter of calibration, relative calibration between the two, and not some funny physics going along the way. So then people tried, yes, yeah. Yeah, so then you would need to preserve the CMB photons, and you would need to argue that the CMB, the photon we see from CMB and supernovae are at very different momenta, wavelengths, and that some are affected and some not because of the different frequencies. Because if you would have an effect like this for the CMB, I mean, most probably it would produce some non-thermal distortion of the CMB. Yeah. So I think really it's not a promising avenue at all for all these reasons. In category 3, you say, okay, it's really a calibration issue, and the problem is with the calibration to the sound horizon. So we must find a way to make a different prediction for the sound horizon. In the sound horizon, there are 3 ingredients. There is a redshift of decoupling, which gives you the boundary of this integral. There is a sound speed in the tightly coupled photon baryon fluid. And there is the expansion rate before decoupling, before recombination. And so you can play with either of the 3. And the first possibility is to play with the redshift of decoupling. So you need to shift the time of recombination. And people tried to do this in order to have decoupling taking place earlier. If it takes place earlier, then clearly the sound horizon is smaller. And because you measure the ratio of dA over ds, if ds is smaller, dA needs to be smaller. The red point will go down and will eventually be compatible with the blue points. Okay, so people have tried this in different ways. It's not easy because recombination is very constrained by our precise knowledge of the hydrogen atom. It depends essentially on transition level between excited state of the hydrogen atom. One way to do it is to play with inhomogeneous recombination in the same way that Matteo talked about inhomogeneous rayonization, which can be motivated by having a very strong perturbations on small scales not visible in the CMB range from, for instance, primordial magnetic fields. Or you could assume that the physics of recombination is really described by the equation of the standard model, but some fundamental constants have changed their value between recombination and today. And there are models where, due to some new physics, either stringy physics or Higgs-like physics with light degrees of freedom, you can have a small drift of some constants. If you have a drift of some constants, cosmology will be insensitive to most of them, with a few exceptions like the electron mass or the fine structure constant. And for instance, if the electron mass had a drift and decreased by 0.5% between recombination and today, then maybe you can shift recombination in such a way to make the 2 datasets agree. The problem with all these models is that they might be successful, but you really need to do a dedicated fit to be sure, because when you shift recombination, yes, you change the sound horizon, but there are other effects in the detailed shape of the CMB and matter power spectrum, which could be annoying and which could ruin the good fit to CMB and large-scale structure data. And we will see later with a dedicated fit that this idea works only due to some, up to some extent. And the last category, category 4, consists in playing with the expansion rate in the early universe. So I will not explore the possibility to play with the sound speed itself. There are no proposals on the market, but who knows, maybe somebody will get a very good idea, but it's not so obvious to change the sound speed in the baryon photon fluid because it's given by very simple physics and equations. So let's see what happens if we want to play with the expansion rate in the early universe. Then the idea is that if you have more expansion in the early universe before recombination, then H is in the denominator, so ds will decrease. And so for the same reason as before, dA will decrease and the red will move back to the blue. And so people try to do this, but with the constraint that H of Z cannot be very different from the standard model at earlier time, at BBN time, because then you would have problem to explain the observed abundance of helium, which is compatible with an effective neutrino number of about 3. So you need a mechanism where H of Z is enhanced before recombination, but not in a significant way at BBN. So it needs to be a kind of transient enhancement. People try to do it with these, all these stepped dark radiation model where you have some form of entropy release, you play with dark energy or neutrinos or dark matter or new fields in order to have an NF which is not too enhanced at BBN and enhance much more after. It has been done a lot by the group of Aloni and Schmab in the room, and Buenabad and Neil and others. Then there are the models of early dark energy, where you have a scalar field, maybe motivated by to make it sound a bit less ad hoc, which would enhance the density, total density of matter in the universe for a short period of time before decoupling. There are lots of implementations of this model. And finally, there is a variation over early dark energy, where you say that the scalar field responsible for these enhancements is actually part of the geometry, like in a Bronx-Dickey theory, is part of the gravitational sector, and then it would be an early modified gravity. And the Bologna group is very active on this. Okay, but here again, if you play with these ingredients, you might solve the DS problem, but you will also introduce other small effects that will leave a track in the detailed full shape of CMB and matter power spectrum, and which might ruin your fit. So to be sure, you need to do a dedicated fit. So these are general categories. Now, if you go to specific model, there is an incredible number of them. This was already a list of all proposals in 2021 in this review, has been updated by this Cosmoverse collaboration with even more possibility. And each of these lines is a proposal, is a paper with a prediction for H0. Now, this is very nice to do such review because you get a view on all the ideas that have been proposed. But the problem, if you quote the H0 found by each paper, is that you are not sure that all people are using the same data. And very often, people tend to consciously or unconsciously cherry pick the data that is good for their model. So if you want to know if you can really solve the Hubble tension, you should compare all models against the same data set. And this was the starting point of our paper from a few years ago on the Hubble Olympics, where we choose 19 representative models of the previous categories, and we tried to confront it to always the same data set and to use different metrics to quantify the tension. And our conclusions were not too optimistic. We were giving medals to models that could, for which one or two or three of these metrics would reduce the tension from a 5-ish level, sigma level, to a 3-ish sigma level or below. It is not extraordinary. And the model that really did not work were the model where you change the late expansion history. So this was category 1. Models in category 3 and 4 could work a bit better, but the model were the model with a varying electron mass or with an early dark energy, and to some extent, a model with self-interacting dark radiation could also work decently well. Why is it relevant that dark radiation would be self-interacting? Because it's when it's self-interacting, when you increase N effective with a self-interacting relativistic species, you get less bad effects on the high L CMB temperature spectrum than when you increase it with free streaming relativistic species. Okay, so some models were doing okay, but then we retried later with more recent SPT and ICT data, more recent choose data. And in this paper, the models were really struggling. Again, only the model with a varying electron mass could reduce the tension to some extent. Early dark energy was not too bad, but with some caveats. So you see that none of these models is really predicting a large H0 as you would like. They are just increasing the error bars, and not that much. A traditional early dark energy model allows you to explain something like 69, but not really larger than this. And to make the model with a varying electron mass work, you need to combine it with curvature. So which it sounds pretty ugly because already you have to introduce ad hoc and fine-tune physics to have a varying electron mass. And if you introduce omega k on top of this, you abandon the nice minimal paradigm for inflation. So really, these solutions sound very ad hoc. They don't solve the problem in a spectacular way. They are just a way to decrease, motivated by other arguments. So the situation is pretty ugly. And we are doing one more update now. We started a few months ago to work with the same group as in the original Hubble Olympic paper to do an update with even more recent SPT, ACT data, DAISY year 2, and better shoes data. And the situation seems even worse. Really, we don't find any plausible explanation. So maybe we are too shy. We find that each of these models is already a bit ad hoc and fine-tuned. And so we are maybe too shy to combine this ad hoc solution together, but maybe we shouldn't. Maybe a combination of late and early dark energy and shifted recombination would work, but not appealing at all at the moment. So I don't have time. I was going to talk about the situation with neutrino mass, but this is a bit orthogonal. So I will shift the neutrino mass thing and go to my conclusion slides. What shall we do about it? So from what I said, it sounds much more reasonable to assume that the problem is the systematics in the data, right? And most theorists believe this, but it's one thing to believe it and another thing to prove where the problem is in the analysis of the data. And it's very, very tricky. And I showed you that collaborations like SHU, CCHP, they look at lots of possible systematics and they do a very good job in trying to rule them out. And they have really no idea of what could go wrong in their analysis. A bit of hope subsists, in my opinion, from the fact that the analysis of distance ladder is a very, very complicated business. When you are an outsider and you try to understand all the steps of the analysis, you realize that you need to dedicate a year of your life to learn all the steps, and essentially nobody is doing it. So essentially only the people in the collaborations fully understand what they are doing. And even if they do it very well, to the best of their knowledge, it means that there is hope that if some people from outside would look at this pipeline, maybe with their own ideas and their own approach and habit and view on cosmology, maybe they would find something fishy. So we have to push the experts to open their data analysis pipeline and to challenge each other's assumption, and also to let people from other area of cosmology look at all the steps of what they are doing and see if this could be criticized. And we have also to convince the people in the distance ladder community that they will gain more from an approach where you try to find some kind of consensus rather than deadly competition. Maybe you get more funding if you try to agree than if you try to disagree in a way, right? So for this, we need manpower, we need incentive, but the people in the distance ladder collaboration are open to these arguments and are ready to get into this stage if we create an appropriate structure for it. From the point of view of the theorists, what the majority of people have been doing is a top-down approach. You come with a new physics idea, you implement it, you compare it to the data, and see if it works or it doesn't work. And usually, of course, it doesn't work. We should try more to follow another approach that some people are already following, that I would call bottom-up, in which, without being too model dependent, too specific, you look in the data and you compare different information. Maybe you combine different type of observation with each other in order to try to isolate effects. And you say, okay, clearly I have this margin to change the late expansion history and this margin to change the early expansion history, this margin on the sound horizon, etc. And then instead of shooting many bullets in the dark, you would know really what is a combination of ingredients that has maybe a chance to work, if any, and you would think of which model should be designed in order to address the specific problems. So this should be followed more frequently, I think, and it's doable. And then we have to think, and this is my final slide, of other completely independent way, of course, to measure the Hubble tension. And there are many people are proposing an approach which is like a single step ladder. You don't need to calibrate objects to each other. If you make very good observation of water mega masers in some AGNs, you will directly get from single kinds of object an estimate of the luminosity distance at some redshifts. You can also look at lensing time delays in quasars and supernovae. This has been done by famous collaboration, Holico, TD Cosmo, but there is a big margin of improvement there, although the systematics are very difficult in this case. There are other techniques where you look at the age of specific object with these cosmic clocks or chronometers. Instead of reconstructing distance to redshift relation, you try to reconstruct a time to redshift relation, and it brings complementary information. And then there are other calibrators that could be used, or standard candles, gamma ray bursts, standard sirens in the future are very promising. There you measure the luminosity distance probed not by photons but by gravitons. And even at some point, our best telescope will make such sensitive measurement of redshift that at some point we will have a completely direct measurement of the expansion of the universe from redshift drifts, meaning that we compare the precise redshift of the same object at a distance of 10 years, and if the measurements are insanely good, you start to see a small drift caused by the expansion. This will happen at some point. Then it will be really interesting to compare these different distances. And maybe if suppose they would all agree with the low H0, then you would have a strong indication that there is a problem with the supernova technique. But it could be that some agree with one, some agree with the other, and then you know what you have to do. Maybe you have a different propagation for photon and graviton, maybe violate the distance duality relation. Maybe it's a problem between early and late universe, maybe between angular and luminosity distance. You would have a diagnosis. So all this will be done, I believe, and but I have no idea when the problem will be solved. It's a tough problem, and it will still take quite some time, probably. Thank you. Yeah. So if you try to fit better the DAISY result with dynamical dark energy, the tension becomes slightly worse. H0 from DAISY goes slightly down. So it's good for reconciling neutrino masses with laboratory bounds, but it's bad for the Hubble tension. Yeah. So the CCHP data alone is not conclusive and not sufficient to claim attention, for sure. Yeah. 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 Thank you. Yeah. No, that's what I was highlighting with this category 1 of models. You have redundant information on DA and DL at the same redshift, so there is no longer any hope that by changing the expansion rate after recombination, you could fit all the data, unless the calibration of one of the two data sets is wrong, unless MB from shoes or DS from other techniques is wrong. At earlier times. Yes, at earlier times, early dark energy is doing this to some general designer. So you could try to just parameterize your H of Z around and before recombination and see the envelope that is compatible with the data. And then you would find that you need a little bump, and you could try to determine in a model independent way how high and how wide this bump would be. I don't know if this has been done or not, but the problem is that the analysis we have done of specific models suggests that this will allow you to go up to an age of 69, 70, but not larger. So if there would be really no issue with the shoes analysis, you would end up still with a 2.5 to 3 sigma tension, which might be okay. Yeah. Or no, nobody came with such a model. What you would, the dream situation is you have a brilliant idea that solves another problem in physics. And if this idea is true, then whatever you do with your parameter, you need to get a larger H naught. Nobody ever found such a model. Yeah. Or maybe some papers have claimed this and turned out to be wrong. Or, yeah. 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 Yeah, the mirror universe. So they are. So this is investigated by Francis C. Racine and Lloyd Knox. But then at some point they need to fine-tune things because of the Boltzmann scattering rate and things like this. Thomson scattering rate. Yeah. Yeah. Scrutinizing. I didn't get your question. Sorry. But are you asking about uncertainties in supernova physics or? Yeah, dust extinction would solve the problem if, but okay, but according to distance ladder people, it cannot, from the observation we have at different frequencies, it cannot be there. But then the problem is, you could say, okay, we don't understand supernova explosion well enough, that's for sure. But you don't really need in this technique to understand supernova explosion, because the calibration of supernova is a completely empirical model. You just prove that there is a scaling between extinction time and luminosity. And once you have proved it, you don't even need to master and understand all the details of supernova explosions. So if you want to get rid of supernova, there are techniques that I showed in slide 3, but they are quite different. You cannot say, okay, I'm going to stick to the distance ladder, but with only Cepheids. Well, it's an interesting question, because there was a paper this summer from a group, mainly European, saying, okay, we get a large H naught only from Cepheids. This is a paper from beginning of September. It's a bit mysterious for me, this paper, because if you have only Cepheids, you have observation only up to a redshift of 10 to the minus 2, and your objects are not really in the Hubble flow. They are dominated by peculiar velocities. So there is this group claiming a high H not only from Cepheids, but I don't know what to do with it. I wouldn't take it to. Yeah. Yeah, the goal would be to scrutinize the first and second run. Really, that would be, I think, the way to maybe find an issue. Yeah. Yeah. Okay. So I can summarize quickly, but okay, most people are aware of this, right? So neutrino mass is can be constrained using cosmology with different effects, and which effect gives you the strongest constraint depends on the epoch and the observation. And we live in an epoch in which the major constraint comes from the background effect of the neutrino mass on the angular diameter distance to the CMB last scattering surface and from CMB lensing. And both are pushing for a small neutrino mass because from CMB lensing, in order to get the right scale of the CMB peak and be compatible with CMB lensing, you have to be in this line. But because CMB lensing is so strong, you have a very strong upper bound. And then in order to be compatible with the expansion rate probed by DAISY, you need to be now in this orange band, which is a bit larger, up higher than before. And the overlap is very small. And that's why we have a very strong neutrino mass bound now, which is embarrassing. But of course, we are anyway very far from shoes. And so people have played with this inverse effect of the neutrino mass that they call negative neutrino mass. And then if you take DAISY and CMB data, you would find a small anti-neutrino mass effect is preferred. But this would still be far from reconciling anything with shoes that would need a huge anti-neutrino effect. Yeah. And when you open up for dynamical dark energy, you move the orange band down, actually. And so DAISY and CMB become compatible with a more reasonable value of the neutrino mass, around 0.06, 0.1. However, this is doing nothing towards solving the Hubble tension, which subsists and which is, as we were saying, even a little bit stronger in this case.